Hi guys, thanks so much for watching the video. I had a great time hacking um, the last few days, and I'm an engineer by training. I did a PhD in computer science from Carnegie Mellon. My background is in machine learning, algorithms, data, that sort of stuff. So today I want to talk about a platform that I built called simulateanything.com, where people can go in and write their own simulations. Lowering the bar significantly to write a new simulation. But much more importantly, it's a place where people can share their simulations and play around with it. So anyone can go in and play around with it, change the parameters of the simulation, even change the source code of the simulation, create their own version, and save it and fork it and so on. So the high level idea is, let's say you look at a standard simulation. So this is one of the gold standard simulations that's been done to forecast the impact on hospitals for COVID-19. This is pretty standard. Anyone writes simulation, they publish a paper, and it has a whole bunch of results about it, and a whole bunch of parameters and assumptions that went in. So we don't really have a healthy way to play with that or even disagree with it. If I disagree with it, it's practically impossible for me to go find the source code, reproduce the whole data, then actually change the source code, create a new parameter, change an assumption, then show that the results would change. And if I need to show that, the only way is for me to go and create a new write-up and host the source code somewhere else and so on. It's pretty painful, and nobody can play with it. So that's the whole idea of this platform. It's called simulateanything.com. Anyone can go in, write the simulation. All the source code is in here, all the output is in here, and all the parameters are in here. So in this platform, as an example, I wrote a simulation to illustrate the point of social distancing. You would have seen some similar simulations on 2D plots of people moving around the 2D, sort of random walk on a 2D plane. This is similar, but it's much more sort of scientific and not a 2D plane. And so there's description on the left, and it talks through what the simulation is. And then in here in the middle is all the source code, the complete source code. So it has the initial state, which is what the starting part of the simulation is, and then has the simulation loop. This is what gets repeated over and over again. And then the metrics, the set of things that we want to measure. So as part of the platform, so you get this, and then on top of that, you get a small set of, at least for now, a small set of helper functions to help you do the simulations. The helper functions come in a variety of different forms. Some are statistical, such as this sample function here, but some are helping set up the simulation from a UI standpoint. So for example, this radio button and text box and so on. So if you look at this initial state, the way you create this radio button called an interaction model is literally just simple. It is just one line. You just say, I want a radio button, and I want a name to be interaction model, and it can take two values, global and neighborhood. And that's it. You get a radio button, and the model contains the value that the user selected. Very simple, very easy. Same with the text box in here, and so on. We also have some functions for charting. So this is the scatter graph function. So the metrics that we want to monitor, there's the scatter graph. So, and then some simulation and stats measurements in here. That's a very simple starting point. So anyone can create the simulation, but like I mentioned, you can go in and change the simulation. You can add something, and then you can basically save. You get a new version. You can fork it. You can create a brand new simulation. And the idea is, first of all, the parameters of the simulation are exposed. So you can basically say, I want to go from a global model, so this is random people without social distancing, to a neighborhood model, and I can just read on the simulation, and you read on the simulation with the neighborhood model now. And you can change the parameters. So in fact, I'll stop the simulation. We know that the incubation period is actually not 4. The incubation period is 5. We know the mortality rate is probably not a percentage point. It's probably 1.5%. you cannot quarantine everyone who's sick. So let's say that you quarantine half the people that are sick, and then now you can rerun the simulation, and you get a new simulation with the number of days elapsed, a number of people getting infected by the days, and number of people dead, and so on. I don't want to just focus on this simulation because the idea is the platform itself and not the simulation specifically. But at the same time, let me walk through a few things that you can do with this. The next 7-day forecast is a simulation that I wrote where you can take the last 4 days data and then extrapolate from it the next 7 days. And as we speak, it looks like the US cases are maybe flattening a little bit, so there is some hope. So this is the last 4 days worth of data that we are pulling in. So it's 68,000, then it went to 85,000 case count, 123,000 and 141,000. And assuming that is the case, then I did some math to fit this, and that's the beauty of it. If you disagree with the math, go for it. I mean, all that you need to do is hit the fork button, and now it's a completely different simulation that you actually just forked. And then you are basically saying, oh, I don't believe this math, and I think this should not be a math dot square root of, y2 squared here. It should be something else, I don't know, just make something up. And then basically you can say that that's my new version. I want to save that version, and that's the version that I want to share with other people. And but anyway, so that's the whole idea of this simulation. Another simulation that I wrote is the same thing for China, looking at the last 4 days to show that the US is still growing, but China is completely flattened out. This one I think is going to become more useful as people start to look at a curve flattening going forward, hopefully. You can read through the simulation on the left, but the idea is, okay, so we think from Wuhan, maybe the R naught right now is, in fact, maybe greater than 2. I would say maybe 2.3 or so. In here, I have a conservative estimate of 1.9, and I'm hoping maybe it'll come down to 1.4 in a week, and maybe 1.1 and 0.7 and 0.4. So if that is the case, and you can get some numbers from here, because you can look at Wuhan, then you can look at Italy, and you can look at South Korea, what they've done and what the R naught measured values were there, and then see how that plays out. So you might say that, you know what, I think we can squash this much better than this. This is, I think, is going to be 1.1. And then after that, I think we can already get to 0.8 in here. And I think we can get to 0.5. And then 0.1. And you know what? Contagious period is not 12. That seems like an overestimate. A contagious period is 7. Okay, now what? What happens if I do that? That's the beauty of the simulation. It actually still looks pretty bad, at least if you ask me. It's still a full percentage point of people getting infected. So, but that's the whole point. You might think that the assumptions are wrong, and if the assumptions were too extravagant, and then you go and change some parameters, and then it still kind of looks bad. So that's the whole point of it, which is you don't need to guess what would have happened if their assumptions was not right. You can actually go in and make the change yourself. Another simulation, and this is the last one I wanted to talk about, is in fact the data that I showed you. So this paper basically shows the pressures on the healthcare system, how many incubators you need, how many beds do you need, and so on. And they have this visualization that they have on this data, and this is the output of that data. So what does building this from scratch look like? Well, we can actually just go in and reproduce the whole simulation, which is what we've done here. And they themselves do have a median, conservative, and an aggressive base case model. I don't want to talk through the simulation itself, but long story short, you can come up with the same set of parameters. Most of them are matched up with what they were using, such as 54% of the ICU patients needing a ventilator and so on. And if you can, see that there is the peak beds needed is about 230,000, and then we are running short by this model about 48,000, and you can match that up with the data that they have, which is 49,000 bed shortage, 232,000, 34,000 ICU or 35,000 ICU beds for 15,000 short, 35,000 ICU beds, 15,000 short, and so on. But once again, you can basically say, you know what, we have new data coming in, and their model used 8 days of hospitalization. We have much better data. This is already outdated by a week. So as you get new data, you're asking what did the paper do? Because I want to reproduce that data, but actually the hospitalization length is much worse than what we thought. What happens then for all your simulation? Imagine doing this in their paper. It is such a pain. It is practically impossible. There's nothing to play around here, right? But instead, if you were in the simulation, all that you need to do is just go adjust these parameters, and you can go just rerun the simulation in a click of a button. If someone comes in and says, I want a better model, you can actually just, again, fork this thing, um, build a better model, or measure a new metric that you want. It's just fairly straightforward to do it. So that's the whole point of this platform. I'll leave you with actually showing how to write a simulation, because it is quite easy. So we'll just create a new simulation, and then we can enter a simulation title. So coin toss example, just to keep things simple. Measure number of heads of an unbiased coin toss. And then we can just save this, and then if you save it and then if you reload it, that thing still is the same. So that's good. So this thing is now saved. And you can obviously keep updating it anytime you want. Initial state, I'm basically going to try to create a text box that says what the heads bias is. Then I'm going to call it 0.4. It's slightly a biased coin, so that's heads bias. And then you would run it, and then you get your text box with the 0.4, and that's all done. And so I would say num heads is 0, num tosses is 0, and inside the simulation loop, I'm going to say plus plus num tosses. Actually, I'm going to do toss equals, and recall that we have the sample conveniently, so I'm going to say sample of heads or tails with probabilities being, I think I said heads bias, and 1 minus heads bias. And that gives me a sample of a toss, and then I'm just going to say if toss equals heads, then I'm going to say plus plus num heads, and num heads, num tosses, num heads, num tosses. Just run that. Hopefully it all runs. And then what we want to measure is num tosses and num heads, and boom, there you go. So this is the number of iterations. So it runs it 10 times, but we can change that to 100. We'll save it for good measure, and then we rerun it, and now you have 100 tosses and 43 heads that we got. On top of that, like I mentioned, we have some helper functions as well here on graphing the output. So we can basically say heads tracker, create an empty array, and then in here we say num heads is num heads, and then num tosses is and then we can simply say I want a graph of it. So we'll just say scatter graph of heads tracker. I want num tosses on the x-axis, and then num heads on the y-axis. Heads, num tosses, and then that's it. And then we run this, and you get a nice graph, and then above the graph you also have the num tosses, num heads. So that's basically the platform. So hopefully you see that how simple this is to create a new simulation, and you have this link that you can share with someone. Someone goes to that link, obviously, and you have your number of heads simulation for them to go play around with. And they can stop the simulation anytime they want. You can change the parameter to 0.7, and now you should get about 70 heads for 100 tosses, give or take. Um, yeah, the 64. So that's the platform. So hopefully you enjoyed it, and I'm hoping that this becomes bigger than just COVID-19. So that's the long big step, but at least for now, if you can put all the interesting COVID-19 simulations that people might want. If they even request to me, I'm more than happy to put them all in one place and they can share. But I added a couple of generic ones as well. So the hope is that this could be for pedagogy, but it could also be for real big simulations that we want to write, like this paper that actually gets published, where we actually have all the data in one place, have all the code in one place, have all the parameters in one place, and I can actually run the simulation in the same place. So thanks so much, guys. It was so much fun.